All right, third lesson from section 2.2. This one we're going to be looking mostly at comparing average rate of change and instantaneous rate of change. We're also going to get a little look at some position functions, some physics type stuff. So first things first, looking at the average rate of change, which is just the slope formula, y minus y over x minus x. And in order to have this, you would need to know 2 points in order to get the average rate of change. And so if I were to connect the dots between 2 points, I'd be looking at a secant line instead of a tangent line, right? A tangent line only connects at 1 point, which is why we get an instantaneous rate of change when you are talking about derivatives and a tangent line. So let me show you an example here. So if you look at example 1, if I were to find the average rate of change between points A and point B, so I have 2 points, so if I connect the dots on that, I get a secant line because it connects at 2 points. If I were to have a tangent line at point C, you can see it only hits at 1 point. And so if I get the instantaneous rate of change here versus the average rate of change here. Okay, and obviously in this case, you can see that the tangent line has a much steeper slope than the secant line, so the answer for this one would be C. It just has a greater slope at that one. So moving on down to just a common sample problem that you're going to run into that I wanted to give you guys. So for this one, we have a line and a parabola, and those two guys intersect at a single point, and so we get this line as a tangent line to this graph. So what we're trying to figure out is what would K have to be? And so on this one, we're going to end up creating and solving a system of equations in order to do this. And so to get this, here's kind of the first step that we'd want to recognize. A tangent line that connects to a parabola, where they intersect, they would have to have the same y coordinate. If you look at this example right here, you can see this curve and this point where the tangent line hits. If you go straight over, these guys have to have the same y coordinate where they intersect, right? And so this is a point of intersection, so they have to have the same y and the same x, but we can't work with the x's yet, so we're going to work with what we have for the y values. So because that's a point of intersection, I can set this function equal to this function, which looks like this. Sorry, I can set this function equal to this function, which looks like this. And so that gives me one of my setups, but because we have two variables, we're going to need a second equation. And so the other thing we'd have to recognize is these guys would also have to have the same slope at the point of tangency. So I know the slope of the line is obviously -2. The slope of this is going to come from the derivative. So if I multiply my 2 to the front, I have 2k x to the first power. So I'm setting the derivative equal to the slope of the tangent line, and that creates my second equation. So here's those two equations put together, creating our system of equations, and now we can solve this. Probably using substitution would be the easiest way to go on this one. So what we are going to do is on this equation, we're going to get x by itself, which would look like this. And now we can sub this in for x into this equation here and here, right? And so that's what that would look like. And from there, it's just a lot of simplifying. So multiply the -2, square this guy times k, and as you clean all that up and solve for k, this is what it would look like. All right, let me flip the page. All right, example 3. So we're going to do a little comparison here of average rate of change and instantaneous rate of change. So for this guy, we're looking at the function of cosine x, and we are going from 0 to pi over 4. So what we're going to do is we're going to get the instantaneous rate of change at each of those endpoints and compare it to the average rate of change from here to here. And so this is what that would look like. So from 0, sorry, let me try to take off the glare. So at 0, you can see right here, I should expect an average rate of change of 0, because I can see right here there would be that's a maximum. So I would have a horizontal tangent line with a slope of 0. And so we're also going to get the instantaneous rate of change at pi over 4. And then we're going to compare that with the average rate of change. So if I were to connect that point to that point with a secant line, what would be the average rate of change or the rate of change of that secant line? And so that's what we're doing on this one. So first things first, we're going to get just the average rate of change. These are my x's. I would have to plug those into this guy to get my y values. So I'm doing a little y minus y over x minus x. So that's what that would look like. And as I get some real numbers out of my cosine function, it's going to look like this. And that's kind of the best I can do to simplify that one. So not real pretty, but that's our average rate of change. I believe I got it written down here, so that was the negative 0.373 if we were to do that in a calculator. So that's our average rate of change. So we should expect this value to be between the instantaneous rate of change of each of these values right here. So of course, instantaneous rate of change has to come from your derivative. It's the only way to get that. So if we did the derivative of cosine of x, we get the negative sine of x. As I plug in a 0, just like we suspected, I do get a slope of 0. As I plug in pi over 4, I get this. And if you were to put this into a calculator to get a decimal, you can see that our average rate of change is between the instantaneous rate of change on those guys. So this would be like the sort of the secant line, the slope of the secant line between those 2 points, which would be this guy. Okay, so moving on down to our example 4 here. All right, here we go. So we are on this one looking for the equation of a tangent line. So right off the bat, we should be thinking point slope. Need a point, need a slope, and then we can plug it into our point slope formula. So we got to just take whatever information is given to us and come up with our point and our slope. One thing that's really important on this is, so here's the function, the square root of x. That's this one right here. This is our square root of x. We are given the point negative 4, 0. Understand that negative 4, 0 is not on the square root of x, right? And so this is not the point I can use in my point slope function. What we have to come up with is the point of tangency, which is right here, right? Those are the coordinates that we would need in order to plug into our point slope formula. So that was this little side note that you see here. So what I did was plot the point negative 4, 0 and just drew as best as I could what would be a tangent line to the square root of x. And then we need to come up with these guys right here. All right, so in order to come up with our slope on this, as always, we would need our derivative. So if we think of this as x to the 1/2 and get the derivative on that, this is just one way you could write it. You wouldn't have to put it in this form necessarily. But anyway, let's take a look at the points we were working with here. So on this tangent line that I'm trying to find the equation of, we do know one point on that is at negative 4, 0. Where it hits, we're just giving sort of a general expression for that. So this is our x coordinate. We're just calling that x. The y coordinate would just be the square root of x. It's just the function itself, right? Think of this as y equals the square root of x. So this is our y coordinate. And so here's what we have. We have our x and y here. We have another xy ordered pair here. And so we're just putting that into our slope formula, which would look like this. And if we clean that up as best we can, we come away with x equals 4. So our x coordinate we just figured out is 4 at our point of tangency. So right here we have x equals 4. Of course, if I plug that 4 into my function, I have the square root of 4, which would be 2. So at 4, 2, right there we have our point of tangency. So let me come on down here. So we now have our point to go into our point slope formula. We just now need the slope. And so if we take our derivative and we plug our x coordinate into the derivative, that's going to give you your slope. And just like that, we're right back into our point slope form. So y minus y equals m times x minus x. And always better to put that into slope-intercept form, which would look like this. All right, one more page here. Let me flip this over and give you this last part. So on this one, we are looking for the tangent line, two different tangent lines. So we need two equations on this one. And what we are told is this is the general function, y equals x squared, and it's the two tangent lines must pass through the point 1, negative 3. So let me give you a little visual here. So here's the overall function of y equals x squared. Here's the point 1, negative 3. And as you can see from here, I can easily draw a tangent line right there that passes through 1, negative 3. I can also draw a second tangent line right here that also passes through 1, negative 3. And so our goal is to get the equation of those two dotted lines. So first things first, we're going to need to come up with some slopes. We're going to need to come up with these points right here, these points of tangency we're going to need in order to plug into our point slope formula. And so first thing we did on this was real similar to the last one. This is your point that is on each of those lines. And so if I just take the general setup like we did in the last problem, where x is our x coordinate and the function x squared would be the y coordinate, then I can plug, if I take this point and this point, plug that into my slope formula. So I'm looking at y minus y over x minus x. And if you simplify all that, keep in mind on this that the slope between those 2 points must equal the derivative, right? Because our derivative function is our slope function. So if we take the derivative of this, which is 2x, it must equal the y minus y over x minus x from our slope formula. And so here's like the equation that we're setting up right there. As you go through and solve this little quadratic here, when you get to the point where you put everything onto one side to make it equal 0, then you can factor it and you get your two x values, which are the positive 3 and negative 1. So I know at negative 1 I have a point of tangency, and positive 3 I have a point of tangency. And so from there we would just need to come up with their y coordinates, which you're always going to get from the original equation here. So I'm going to plug negative 1 into this and 3 into this in order to get this information that you're seeing right here. Now that we have our points, all I would need is the slope of each line in order to get our point slope setups. And of course, this is where the derivative comes into play. So if I were to plug negative 1 into my derivative, I get a slope at negative 2. If I plug 3 into my derivative, I get a slope of 6. And so here's all that information put into two different point slope layouts. And so from there, obviously, if you wanted to get y by itself, you certainly could. Let me give you one last problem here, and we'll call it a day. Okay, a little fun with physics here on the final example. So looking at velocity and position or distance, same thing. So a couple things to point out on this. For one, when you have a distance or a position function like this, so this is just a general quadratic layout for a position function or a distance function. So one thing to note is when you take the derivative of your distance function, you get velocity. And then we'll look at later, if you take the derivative of velocity, you get acceleration. So the rate of change of distance is velocity. So that's kind of what we need to know for this one. And so what we're looking at on this one is, here is our general layout for the distance or the position function. A couple things to note. The g is our gravity constant. So if we're talking about falling objects here, obviously gravity has to factor into that. So this is our gravity constant. When you are in feet per second squared, we're using this guy. And when you're in meters, we're going to be using this guy. Okay, and then v sub 0 would be our initial velocity, and s sub 0 would be our initial position. And this one you can kind of remember if you were, say, dropping this from a certain height. Well, the initial position would be however high you are. because at that point time would be 0. So this would go away, this would go away. So the initial height would equal that distance that it's going to travel for those two guys right there. So let's throw in a couple things into this. So if a ball was dropped, so again, initial velocity is going to be 0 for this. So that's going to be 0. From the top of a 100-foot tall building. So all this stuff we're getting right off the bat that we can plug into this function here. So 100 feet is our initial position that we're seeing right here. So 100 is going to go in for S sub 0. V sub 0, again, is going to be 0, right? Because if it's being dropped, not thrown, then it's going to start out with a 0 velocity, like you're just holding it still and letting it go. Right, and then our gravity constant on this one, we're going to use the negative 32 feet per second squared, since this is given to us in terms of feet. And so that's going to go in as our gravity constant. So if we sub in all of that information, we're going to get this stuff right here. And this is after it's been cleaned up a little bit. So you have the 1/2 with the negative 32. That's giving you the negative 16. Since our initial velocity was 0, that middle term goes away. And we're just looking at here our initial position. All right, so we're just setting this guy equal to 0 so we can solve our quadratic for time. So just subtract that 100, divide by negative 16, and then square root. And we get our time of 2.5 seconds. Recognize on this that t is our x coordinate, and this is going to be our y coordinate that we're looking at right here. So based on this, we just came up with that x coordinate. So if we now take that 2.5 and plug it into our derivative, we're going to get our instant rate of change when this thing hits the ground. So as this thing travels that 100 feet, it started out with an initial velocity of 0. Obviously, due to gravity, it's going to be picking up speed as it falls. Based on this, we saw that it's going to fall for 2.5 seconds just before it hits the ground. And as you take that 2.5 and plug it into your derivative, this is based on this derivative function, this is the speed that it's traveling as it hits the ground, right before it comes to rest again. So, and then we're seeing that as a negative because you're heading in that downward direction.